Okay, good afternoon, everybody. Welcome to this GReTA seminar. Today, the speaker is Reiko Heckel, professor at Leicester University. I think that Reiko doesn't need an introduction. He's one of the leading persons of the graph transformation community and also one of the organizers of this series of talks about graph transformation and related topics. So in the talk of today, Reiko will present an application of verification techniques based on graph transformation for visual smart contracts using the DAML language and exploiting the Groove tool developed by Aaron Rensing and his group. Reiko, I think you can go on, please.
Okay, excellent. Thank you very much, Andrea. As you know, the original talk proposed here or advertised for this slot was about Groove. So I thought I'd do something that sort of combines the recent talk I gave with at ICGT, which happens to apply Groove for some verification purposes, with a little sort of mini tutorial, sort of another example in Groove that helps you to understand the concepts there, in case you're not familiar with them. So you get at least a little bit of an overview of Groove, even if it's not at the same level as you would have, obviously, if you have a whole sort of session on Groove. So, but let's start with the motivations first, and we'll come to Groove when it matters. So, the overall question here is about basically quality management or quality control in the development of smart contracts. So smart contracts, I mean, the concept is relatively old, from the 90s or earlier than that, but they have become relatively prominent in the context of blockchain applications, in particular in Ethereum blockchains, where if you think of the blockchain as the underlying database mechanism, so the mechanism to store the database, store the data, the smart contracts, I think the functionality, the operations basically operating on that data. Yeah, so that's how they became prominent in recent years. And the idea is that if you can execute them on the blockchain, they automate workflows, they automate the recording of transactions, so the logging essentially, and therefore they contribute to the overall aim of a blockchain, that you don't need trusted intermediaries for sort of, I mean, on the one hand for storing data, but including the smart contracts also for performing complex transactions. There are a number of different platforms that support smart contracts, depending on what sort of business domain you're in or what kind of specific requirements you have. I mentioned one of them, Ethereum, which I believe is the first one in this sort of blockchain category anyway that uses smart contracts. And because people recognize that, and they also recognize that it's quite difficult to migrate basically from one smart contract platform to another one, they developed something that is called the Digital Asset Modeling Language, DAML, which is a kind of technology independent layer to define smart contracts. And by technology independent, I mean that it can map to different smart contract platforms. So you can write your smart contracts in DAML, and then you can compile them essentially onto different platforms like Ethereum, for example. Okay, so this is very good because it sort of makes this kind of technology independent. But of course, DAML itself is a complex language and is a textual language, basically based on a functional programming language based on Haskell. That is not naturally aligned with kind of concepts of objects and components. It doesn't sort of have a natural connection to kind of mainstream modeling languages like UML sort of object-oriented languages would have. Well, it has a relatively clearly, I mean, obviously it has a well-defined semantics, but not one that is defined in abstract terms, in abstract mathematical terms, and so not a formal operation of semantics. So these are the things that we want to address here in this talk. And we do that essentially in a case study, which we're going to pick up a case study that was actually used in DAML as a kind of tutorial, and show how such a connection could be done. Okay, so what we're going to do is we're starting from DAML, this smart contract language, and we're mapping this to typed graph transformation systems that are basically providing the semantic level, the executable level, and we're on the way introducing what we call visual contracts. So visual contracts are a language that basically is a diagrammatic representation of operations on complex data structures that can be used as models. Yeah, and you see there's a close connection to graph transformation, but it's not exactly the same. Okay, so what we are doing is, we're, as I said, starting from DAML structure. So we basically do this twice. Once for the structural part, so the DAML structures, the data structures there are going to be mapped to class diagrams and then to type graphs. The type graphs are the graph representation. And the choices are the operations in DAML, so they are mapped to visual contracts that describe how these operations work, and then later on to graph transformation rules. Okay, so that's the plan. And we're going to do that supporting and elaborating on sort of interesting features of DAML, which make this language useful and sort of effective for smart contracts. So there is a sophisticated mechanism for role-based access control that is built into the language. There is support for management of contracts and sort of updates and archival of contracts, because like in sort of blockchain applications in general, the contracts to the data basically that we have is immutable. Yeah, so you cannot directly change your data, but what you can do is you can create a new version of the data and also store that in your blockchain and archive the old version. Okay, so you basically have the update mechanism instead of, if you like, destructive updates that you would have in a regular database. Yeah, and there are some subtleties to go with that, which we'll come back to later, the sort of pre and post consuming behavior, which is basically the question whether you execute operations on the old version of the contract or the new version of the contract. Yeah, but we come back to that in a moment. And all of this will be supported by analyzing certain properties of these systems using the Groove model checker. So this is where Groove comes in. And before I go into the actual DAML and smart contract discussion, I will therefore say a few words about Groove and show you a little example that kind of prepares in a way the case study I want to introduce, but is simpler so we can actually understand it. So Groove is the acronym stands for Graphs for Object-Oriented Verification. It was introduced by Arend Rensink and developed by him and his students in Twente over many years, probably at least 15 years now, if not 20 years. And the original idea really was to use graphs and graph rewriting as a semantic level for Java, for object-oriented programming. Yeah, so that Java programs can be translated into graph transformation systems in Groove, and then they can be analyzed there. So that was the original motivation. And so in that sense, we are very much in line with that, because we are doing something similar, except that we are not working directly on object-oriented languages, but on a smart contract language. Yeah, but we're also translating that into a Groove model in the end in order for verification. On the conceptual side, if you try to understand what this tool actually does or what it gives you, is it allows to edit graph transformation systems. So generally, you could say it implements typed attributed graph transformations. We'll see in a moment what that means in detail. But that includes type graphs. So graph schema can be edited. You can create and edit rules. You can create instance graphs, so sample graphs, and you can write control programs. Yeah, so that's on the editing side. You can explore these things. So that means you can test them, debug them manually by trying out different rules on different graphs and see what happens. And you can also explore automatically in order to generate, for example, the state space, which can then be used for verification, in particular for model checking, temporal logic formulas. So you can analyze your system using that. Okay, so that's the kind of very high level overview of the main functionality. So let me show you. So that's the web page that I just referred to. So you find lots of sort of documentation, examples, some videos explaining how to use that on that web page. But I wanted to show you, as I said, a little example. And this is a very simple voting system that I want to show you. Okay, so we have different parts here of a graph transformation system. And the thing to start with typically is the type graph. So if you know about class diagrams, think of this as a class diagram. Okay, so a voting system here is a very simple one. So voters can vote for motions. Yeah, so a motion is something like a proposal for something to be voted on. So a voter can support a proposal, for example, and can be invited to vote on a proposal. Okay, and the motion, the proposal itself, has two attributes. One is invites, is basically counting the number of voters that have been invited, and there is a count, which is the number of voters that have supported the motion. Okay, so in this way, we should be able to work out whether the motion has passed or not, so whether you won the vote or not. Okay, so that is my type graph. Yeah, and now I need to specify the actual operations, the actions that allow me to do the voting and to basically manage the voting process. And this is done by means of so-called graph transformation rules. So this is a very simple example of a graph transformation rule that just creates a new motion. So the notation here is that everything in green, as you can see, the motion here is created. So without any sort of particular context, I can create a new motion and set the count and the invites to 0 in that process. But I can only do that if I haven't got a motion yet. Yeah, so the red motion here represents what is called a negative application condition, which says that I can only do that if I don't have a motion yet. So the idea here is that I can only have one motion at a time. Okay. Then I have a rule in order to send out invites. So I need to have a voter and I need to have a motion such that, and again, I have a negative condition here. The voter hasn't supported the motion yet, so hasn't voted on it yet, and also the voter hasn't been invited yet, yeah, because we don't want to invite the voter twice, and in that case we can invite them. Okay, and in the process we can update the number of invites because we basically increase the invites to by 1 here. Yeah, because we need to keep track of how many we invited. Yeah, so that's the invite rule, and then we have a rule for voting. So a voter can support if you have a voter and a motion, and the voter has been invited, then we can create a supports edge here, which means the voter has voted in favor of the motion. The reason that the edge here from the motion to the voter, the invited link here is blue, is that it gets deleted in that process. So if we vote, then the invite link is deleted, and the supports link here is created. Okay, so that's the whole model. So that means we have our type graph or schema. We have 3 operations here. We also need a start graph. So basically, we need to define the initial state. So the initial state here is just a simple one with 3 voters. Okay. So this is how we are going to start. And now we want to start applying our operations. Okay. And the first thing, obviously, we need to do is to create a motion. Didn't I just order this? So creating a motion, as I said, doesn't require any preconditions. So we just execute this operation, and then we have a motion here. Okay. So that's what happened in the first operation. Oops, where's my other voter? Oh, I don't know what happened here. Okay, so now we have a motion and 3 voters. Now we want to send out invites. Okay, and the send invites rule, as you see, need to pick a voter and a motion and then create this invite edge. Yeah, and if you look at the left pane here, you can see the send invite operation, and then you can see 1, 2, 3 options here, which are the 3 different places, the 3 different matches where I can apply this rule. Yeah, and I can say, for example, I want to invite that middle voter there, and now this match is gone because I have created that invite node, that invite edge, and I don't want to create another one. Yeah, I only want to create one per voter. Yeah, so I can invite the other 2 as well. And now you can see that the send invite rule is not enabled anymore. So it doesn't have any more matches listed underneath it, as well as the create motion rule that I had earlier. Now I can start voting. Yeah, and every vote basically now means that a voter supports the motion. I don't have a rule here for rejecting the motion. The assumption is that voters support the motion, and then eventually voting finishes. And then if I have enough support, then the motion is carried, and otherwise it is not. Okay, so that's the idea here. So now I can sort of say, for example, the first voter here could now vote in favor of the motion. Okay, so it's done that. So the invited edge is replaced by the supports edge. And if you look at the counters here, I didn't say that, but the invites counter went up to 3 because I invited 3 voters, and the count now of the support went to 1. Yeah, because I had 1 support. I have 2 possible further voters that can support the motion. So let's say that one supports the motion as well. Okay. And now, as you would expect, you have 2 voters supporting that and 1 voter who hasn't said anything, but the motion is already carried. Yeah, the motion is won basically. I have a little pattern here, a little condition that can check that. So if this condition is it's like a rule without a match. If this condition is it's like a rule without an effect, which is just the left-hand side. It's just a pattern. So if there are twice as many supporters or more than twice as many supporters as there are invites, then the motion is carried. Okay, so let me just slightly puzzled now, but anyway, right. So that's basically a condition that tells me that the motion is carried. Okay, right. So that's what I said earlier. So I can create graphs, I can create rules, I can simulate the rules manually, but I can also simulate the rules automatically. And to do that, so let me just start from the beginning again. I can look at the transition system. So the transition system is basically records all the states and all the transitions in the system. So the complete state space, the complete behavior of the system, which is possible in this case because it's very simple. At the moment, I only have the start state again. So I basically initialize the system with the start state. Okay, so the start state can then be explored and sort of lead to all the other states. And I can now generate all the state space, all the possible states and transitions. And I get this kind of little transition system that you can see here. So I see all the possible things I can do. From the start state, I can create a motion only once. If you've seen that, then I can send invites. There are 3 different possible ways in which I can send invites, as you can see. Then once I've sent 1 invite, I have 2 more ways to send invites. And then I have 1 more way to send invites. And then I can start voting. And you can see that I can do things in a slightly different order, but eventually I will always end up, if I execute all the rules that I have as much as possible, I end up in a situation where the motion was carried. Yeah, so this is visible here in the end state by the label carried, which says that this condition here was satisfied in the end. Yeah, and we can analyze this automatically as well. So this is now, sorry, this window got in the way of my, let me put that here. So we can also verify this automatically. We can write a formula here. So this is a temporal formula in a language called CTL, computation tree logic, which defines properties over computations. And AF here means, so the A means that this property holds for all possible branches in our computation. And F means that eventually, finally, at some point in time, in any of those branches, the motion will be carried. Okay, so basically the formula says whatever you do, eventually, if you execute everything you can, the motion will be carried. Okay, and we can analyze that, and it tells me, yes, this is true. Okay, so it's not particularly surprising, as I said, because we don't really have a rule to reject or vote against the motion. Yeah, so eventually, if I execute all the rules that I can execute in all possible ways, the motion will be carried. Right, so let's see if we can repair that, yeah, just for the fun of it. So let's create a new rule and say this new rule, let's call that reject, or let's say vote against. Okay, and I mean, that may look similar to the one for voting for. So let me just be lazy and make a copy here. Okay, so now we want to vote against a motion. So how can we do that? Well, we need to rather than create a support edge here, we need to create an edge that we call, let's say, rejects. Okay, and in that case, obviously we don't count this as support, so we leave the attribute, the counting attribute as it was. Okay, so that's okay in principle now, but now it complains and says, well, we've introduced a type here that doesn't exist, so this is an unknown type. We need to introduce that into the type graph. Okay, so we need to edit the type graph and also add rejects here as a possible type. Okay, so so now that should be possible? Okay. Yeah. So now let's try and execute that. So we go back to our transition system and now say we want to run our transition system again. But now you see it started exploring this and generating transitions and states, and it explored it or did it up to 2000 states, and then it stopped and asked me, do you really want to continue? And I don't really want to continue, because as you can see, I already have quite a lot here. It only shows me 100, I think, at the time, but it created 1,000 states and sort of nearly 3,000 transitions. So something has gone wrong here. So this is not what I wanted. Okay, and the reason why it created so many states and transitions is that I basically in this rule here I deleted the invite edge and created the rejects edge. Okay, and that means that the invite rule that I had earlier, this one here, this is now enabled again, because this checks that there isn't an invite yet, and it checks that there isn't a support edge yet, but it doesn't check that there isn't a reject edge yet. Okay, so it's basically creating a cycle here, and then sort of arbitrarily many edges here of type reject. So we need to repair that. So basically, we need to add an additional condition here, saying we must not have a rejects edge either. Yeah, in order to avoid that infinite loop. And now, in principle, we should be able to execute this and get a kind of decent number of states and transitions. Yeah, so now it created 21 states and 51 transitions, as you can see here. So it gets a little bit more complicated than it was before. Okay, because now you also have the option to vote against the motion, not just to vote in favor of the motion. And we see that there are final states now here that do not carry this carried label, which means there are sort of outcomes of my vote where the motion is not carried. And we can explore that again, or sorry, verify that again. You don't believe it. Look at this property again. So now again, we ask, will it always be the case that eventually the motion is carried? And if we check that, it says this property does not hold anymore in the initial state. So not all the outcomes of our vote will be in favor of the motion. There will be some that reject the motion, which is what we want. Okay. So this was just a little exercise to demonstrate some of the features of Groove and how you edit that. I hope that gives you a rough idea. And so with that in mind, you probably have a better chance of understanding what I'm going to do next. So as I said, we want to translate the DAML structures ultimately into type graphs, DAML choices, operations, ultimately into graph transformation rules. So we've seen how these type graphs and graph transformation rules look like. And we want to then use Groove in order to analyze some properties. Yeah, so it's basically a more complicated version of what I just showed you in this very simple example. But the case study here that we've chosen is actually related to voting, except that it's not voting for motions, but voting for sort of slots in a Doodle. So you probably know Doodle as a tool to arrange meetings, which is exactly what we want here. So we have a number of slots, a number of options that we can vote for, and then we record how many people have voted for which option, and then basically we use that option in order to yeah, maybe find a date for our meeting. Okay. So this is, as I said, a case study in DAML that is used in some of the tutorials there. So if you just look at the static side of it, the data structure part of it, this is how you define those structures. So yeah, you can define a data type for something like a voting slot. So a voting slot is, as I said, is an option you can vote for. That has a count because you want to know how many have voted for it. You want to know who has voted for it. So you have a list. There's a list of parties. So parties are basically the agents, the participants in the smart contracts. Yeah. And there's a little bit here about sort of general properties. So what notion of equality is used and so on, which I don't want to get into. Then you have a template for a Doodle. So just to give you an intuition, if you're familiar with object-oriented languages, a template is like a class, okay? And the instances of a template, the objects, are called contracts. Yeah. So this is a language for smart contracts. So the contracts are basically the objects. Okay, and we can translate that the same information into a class diagram, which is shown here. So we have a class voting slot. Okay, which has the count as an attribute, for example, which you can see here. Okay, we have a template, as I said, as a class. We have a sort of a class Doodle, which you can see here. That has a number of attributes that you can see. So ignore the kind of key stereotypes for the moment, but you see the name, the organizer, the voters, the options. No, sorry, you don't see the options. The options are the options. But you see the votes here. The votes is an association here, as you can see. You see a Boolean attribute telling you whether the Doodle is open for voting or not, so whether voting has started essentially. And you have stereotypes here to introduce kind of specific features, because if you look down here, you can see a key phrase here saying that, for example, organizer and name are key. Okay, so organizer and name together form a key. So that's like a key in the database, which we record with this key attribute here. There's also this ensure statement here, which says that voters are unique. And we record that by, we don't record that here in the class diagram. We do that later in a property. Yeah, so you see the votes here, and votes are basically a mapping from options to voting slots, which you see here. Okay, so we can translate the structure that we have here, the data structure, into an object-oriented data structure, basically, that we record here in the class diagram. We also see operations here. So there are operations for adding voters, removing voters, issuing invites to vote, and for voting. Yeah, and an invite itself is a contract, so it also has an invite. Sorry, it also has a template. And that has then also a choice and operation here for voting. Yeah, so we see that in a moment. Okay, so this is how you can use UML class diagrams in order to model the structure basically of these visual contracts. Sorry, of the smart contracts. Yeah, of the DAML contract. Okay, so that's our middle stage. The operational level, the semantic level that we want to represent in Groove. For this structural part is the type graph, and you can see a kind of complicated type graph here. In gray, you see all the structures that we've seen in the class diagram. So you have parties, voting slot, Doodle, and so on. So basically the templates that we talked about. And then you have lots of blue things here on the left and on the right. And they are kind of control structures that are needed in order to manage the execution of operations. Yeah, so we have nodes here that don't represent data, but that represent basically the fact that a certain operation has been called, or that a certain operation has certain input and output parameters and so on. Yeah, or that one operation calls another one, as you can see here with the call edges. Okay, so we need that in order to manage the actual operational semantics. Okay, so we'll see that in a moment. So that's basically what we do on the structural side. And then on the behavioral side, as I said, the operations in DAML are called choices. So the idea is that a contract is created by one party, which is called the signatory of the contract, and then it's used or executed basically by another party, which is called the controller. Okay, and the controller can then execute those choices. Yeah, so I offer you a contract, and then you can execute choices on that contract. That's basically the idea of DAML. Yeah, and this is the choice to add voters on the Doodle contract, and it has input parameters. The operation has input parameter voter. Yeah, so Doodle is the context in which this takes place. So that's already given. It's like the this object, and then voter is a parameter, is an input, and then what do we do? I mean, we first of all check that the organizer is an attribute of Doodle, is in fact the controller here. Okay, so this is just a test to make sure that no one else is executing that choice. And then we basically check that the Doodle is not open yet, because if the voting already is already underway, we don't want to add voters to the contract. So we only do that when it's not open yet. And then we create a new version of this contract. So create this with basically this update. So you basically replace voters by the list of voters by adding a new voter, namely the voter that we got as a parameter here to this list. Okay, so that's what happens. And so this is in DAML. If we write that as a visual contract, in UML notation, essentially, it looks like this. So we say there's the organizer here, who can sort of trigger this operation, where D prime, the new version of the Doodle, is created by basically taking the old version of the Doodle and executing this add voter operation on it with the voter input parameter. And we can write that in the kind of graphical notation by saying we have a transition from the old version to the new version of the Doodle, D to D prime. So that creates a new version, and it only possible if the open attribute is false, and we update the voters on that node. Okay, so that's basically a graphical version of what we've seen in the text. So again, this is the source of the mapping, which is the DAML, the visual kind of modeling UML representation that we would use in a kind of software design process. And then we have the semantic level, which we use for the analysis. And there it gets a little bit more complicated because we do that in a way that sort of works in 3 stages. So we have in an operation, if we execute an operation, there are basically three things that have to happen. The first thing is that we call the operation. Okay, so we create an invocation, an operation call. The second is that we execute the operation, or the sort of the body of the operation. And the third thing is that we return essentially from the call. Yeah, so give the control back. And this is what you see here. So the call so these are three rules in Groove. Okay, the first rule is the call rule. So you see that we have a party and a doodle on which we can execute this call, and another party. So one party is the controller, which is the party that performs this operation. Okay. We create a new we create a call, sort of a call node, which refers to the doodle here as the dis object, or the dis contract in that case. And it also refers to the input parameter, to the voter that we want to add to the list. Okay, so that's our call that we create here. Then we execute that call, and now it gets sort of a little bit more complicated. So this is kind of advanced Groove, if you like. So what happens here is that first of all, we need to find that call, that add voter call. Okay, so this is the one that we've created here. So we need to find that here. We also find the doodle following this link here. We need to make sure that this is the last version of the doodle. So as I said earlier, we cannot delete or update objects or contracts, but we can create new versions of them, and then we need to, first of all, we need to know which version is the latest version, and we need to remember the old ones, basically. So we make sure that this is the latest version of the doodle. We check that open equals false, so the doodle isn't open for voting yet. Okay, we find the voter, the input parameter. Yeah. And then, as you can see, because these lines are blue, we delete these links. Okay. Then we create a new version of the doodle. Yeah, because as I said, we cannot directly change the old version. We have to create a new version. This is then marked as a return. So we add a return link here from the call to this new version of the doodle. We add a link from this new version of the doodle to the new party that we want to add. So voters is basically, we have links to all the voters that are registered, that are registered on the doodle. Okay. We mark this new version as the last version, yeah, and delete the sort of the marker from the other version. So now this new version is the last version, not the other one anymore. And that's essentially it, except that we also have to carry on to carry over all the other information that was already present in the doodle, because we need to basically keep everything else in place. All the other data that is connected to the old doodle need to be copied to the new doodle with the addition of that new voter. Yeah, and this is what you can see here. So this is what makes this a bit complicated. So the doodle here, the old doodle, has connections to a number of voting slots. So these are the different options that we can vote for. And for each of them, we also need to link them to the new doodle. Okay, so this is what you can see here. So this voting slot node here has a little thing attached to it, which looks like a universal quantifier and an @ symbol. So that means that this one here, this node here actually represents the set of all voting slots that is connected to the doodle. And for each of them, we create these votes here. Yeah, so this is a multi-object or set node, as it is called, which sort of allows us to specify a universal operation here. And we do something similar here for the voters. So all the existing voters that are connected to the doodle need to be copied and sort of added to the doodle as well. Okay. So that's essentially it. Yeah, so then we have basically, I mean, we haven't done anything particularly complicated. We just created a copy of our Doodle, copied over all the data, and added the additional voter as a new party. Yeah, and in the process deleted the this edge and the voter edge and the controller edge here because they were just part of the sort of call node that we created here. And then at the end we are applying this rule. So again, we have the Doodle here, which is identified by this return edge now from the add voter call. Yeah, so we created that return edge here, which we now consume. So we delete the call node and we delete the return edge, but we're only allowed to do that if the this node to the Doodle doesn't exist anymore. And in this particular case, this is redundant, but there are other cases where this is necessary. Okay, so that's basically the kind of 3-step process by which we execute this operation, call the operation, execute the operation, and return. Okay, and to make sure that this all happens in this particular order, we have this thing called a recipe that you can see in the top here. So you see that I'm getting slightly confused here. We see the call, the execute, and the return here. Okay. But I'm slightly puzzled here. I think I made a mistake copying that. So what you see here is the recipe for remove voter and not for add voter. I'm sorry for that. Just replace remove by call. Just replace remove by add. So it should be add voter rather than remove voter. Yeah. So there is another rule, another operation that is called remove voter, which works in a sort of similar way. That's where that was copied from. Okay, so I hope that doesn't confuse you too much. The other thing we're saying with these recipes is that when we use this in a moment to generate the state space, the recipe makes sure that this is atomic. So that means there is no intermediate state between the call and the execution and the return. So it's not that we create these states when we execute these things, but these states are not part of the transition system. They're not part of our state space. And that means that we can reduce the size of the state space. We can reduce the number of states very significantly, which means that the analysis becomes feasible. Otherwise, it would just create too many states. Okay? But we know that these things always happen in this order, so there is no point in sort of recording the intermediate states. Okay? How are we doing for time? Okay. So that's one example. Another example is this issuing of invites. This works in a sort of similar way. We want to issue invites to all the voters, and the way to do that is to basically create new contracts, invite contracts for every voter, for every Doodle, or for the Doodle that we are talking about here. And after that, after the issues are after these invites have been issued, we set the Doodle to true. Yeah. So before it was false, and then we set it to true. That means that we can now start voting, and we cannot add any more voters. Okay. So this can be expressed graphically, diagrammatically, as you can see in the bottom here. And then again, there is a translation of that into the actual groove model, which is again in these 3 steps. The first step is to create this, to call the operation, issue invites. The second is to execute it, and the third then is to return from it. There is one additional sort of interesting feature here that is worth mentioning in this rule, because the issue invites call so the issue invites operation, sorry, calls another operation, which you can see here. So the Doodle invite call, and this is the constructor for the Doodle invite contract. So, I mean, okay, so the details may be a bit too complicated to explain now, but basically what happens is that you have a case where one operation calls another operation. Yeah, and that is recorded here. So visually, this is shown, as you see here, by this kind of arrow that goes into this newly created contract. And in the rules, this is basically a new call node that is created by the execution of another operation. Okay, and we again have kind of these universally quantified things going on here, sort of more or less in a similar way, and a new version of the Doodle created and so on. Okay, so that's the kind of slightly more complicated example of the that is sort of similar to the previous case. Okay, we also have the recipe here, and the recipe here contains an operation here that says, or a line here that says, execute this kind of Doodle invite operation for as long as possible. So as many instances of this as possible need to be executed. Okay, so that's the general idea of this mapping. So just to mention one subtlety here, which justifies, I think, the sort of slightly complicated way in which this is represented here. So why we've split this up between the call, the execution, and the return. So there is a difference between in DAML, in the semantics, between sort of different timings about sort of executing operations and changes on the contracts and archiving the contracts. Yeah, so there is a difference between archiving first and executing on the new version, or the other way around, executing on the old version and archiving afterwards. And that makes a difference mostly with the visibility of certain changes in the contract, because some parties have sort of read access to the old version, but not to the new version. Yeah, so this is an important distinction, and in order to make that distinction, it's necessary to basically distinguish between the execution and the archival, and have that in two steps. So here in this case, we see that sort of the archival happens together with the execution. So we basically apply the changes to the new version, but in the other case, we could basically leave the old version and do the archival in the return rule. Yeah, so then we would capture the other semantics. Yeah, and that can be specified as part of the contract. So if you look at this here, this pre-consuming here basically means that it's archiving, archiving first and then executing on the new version, basically, rather than the other way around. Okay. So this is a kind of subtlety, a semantic subtlety that is important in DAML for the access control. Right. So I think I'm slightly running out of time, but let me just say that we can then test this by writing kind of a control script in Groove that looks like this. So we say we create a Doodle. So basically, we have a Doodle call already in our graph. We create a Doodle by executing this call. By executing the Doodle operation and then returning from it. We add a voter, we issue invites, and then we let them vote. Okay, and that basically allows us to implement one particular test case, one particular scenario that we can then take and compare, for example, to what happens in DAML in order to validate that our semantics actually works, so that the model that we created in in Groove actually reflects what should happen in the Doodle, sorry, in the DAML semantics. Okay. So, and in order to do that, again, we need to generate the state space. I can show you that in a moment. And then we can verify a number of properties here. Basically, all these properties that said that certain things need to be unique, we can verify, and we can also verify certain progress properties. For example, it's always possible to reach a state where voting is not possible anymore because everyone has voted already. Okay, we can express that again in certain sort of temporal formulas, which are a bit like the ones that I showed you before. So this, but it's always possible to reach a state where we cannot vote anymore, is the second one here. So it's basically like the one that we saw earlier with the carried, except that there is a negation here. You see an exclamation mark here. Okay, so maybe I can take a couple of minutes to show you how that looks like in Groove. Need to pick up the right version here. Right, so this, what you see here is the type graph that we had earlier. Here you see all the recipes in one big script. Okay, so the add voter recipe, for example, so that's the real one, the correct one, not the one that we saw earlier. Basically says, in order to add voter, you have to call the operation, execute the operation, and return from it. You can also see that we can pass parameters here between them. And this is the test script I mentioned earlier. Yeah, I showed earlier that we can execute. Okay, and we can see the operations here as well. So this is the call operation, call add voters. For example, execute add voter is this one, and so on. Okay. And now we see that because we have these control structures, that none of these operations here is actually executable except for one. So the execute, sorry, I should show the start graph as well. It's that one. So, okay, so what I've done here is I created two options here. So let's say we want to organize a meeting and we want to decide whether we want to do that Monday or Tuesday. And we have three parties here that want to participate in the meeting, and one party is also the organizer of the Doodle. Okay, so they need to vote and need to vote for one of these options, or for both of them if they're available for both of them. Okay, so the Doodle has a name and it's not open yet. Okay, so that's our start graph, and the only thing we can do at this stage, because the control program tells us that, if you look at this, the control program says the only thing we can do, the first thing we can do, is to execute the Doodle constructor, which creates the actual Doodle node, yeah, which we don't have yet. Because if you look at the start graph, we have the Doodle call, so that's the call for the constructor, but we don't have the actual Doodle object, basically. Okay, so we only have the invocation for it. So, but we can execute that, and then we have the Doodle here, the Doodle object, and then we can execute the return. So now, as you see, the return is enabled because that was the second operation in the script that we had. So the return will then delete the Doodle call, the call node, and well, we now have the Doodle connected to the two options. Okay, now we can add a number of voters here, and we can basically, you see a number of different things here, because we can add either voters to different nodes here, to different voting slots here. No, sorry, let me just check that again. Ah, yeah, okay. So there are different matches because I have I have the organizer here as well. So I match two nodes every time. So without going through that now in detail, what I will do is I will just create the state space here. So I see what I've done already in my transition system. So I've just executed two steps here, the doodle and then the execute doodle and then the return. So these were the two operations I applied. So now let's just create a full transition system here. Right, so again, I created 1,000 states and it asked me, do you want any more? Yes, I want more. I want even more than that. And then hopefully it should stop at some point. So we've got 4,000 and it asked me if I want to go to 8,000 states, and I'm feeling lucky today, so let's try that. And in a moment that should hopefully stop. Yeah, okay. So what it's done now is it created kind of 8,000 states in the background and a lot of transitions. It doesn't show them all, but what it actually keeps in the end is just, I mean, you could say 260 states and 700 or so transitions that are, if you like, stable states or states that are not intermediate states. So all the other ones are just intermediate states that are there because basically sort of between the let's say the execution and the return. Okay, but we don't need to remember them. We don't need to keep them because they don't have any sort of meaning in the model. Yeah. So in the transition system here, they are shown as these slightly, I mean, whatever that shape is called, the kind of reddish nodes here. Okay, so they are the intermediate states, and all the other ones, for example, the one here, the closed state or the result state here, these are the actual stable states. Okay, and of those we have 260 only. Yeah. So believe me, if I were to do this without the recipe, so without having this additional control and without basically ignoring these intermediate states, I wouldn't I wouldn't be able to generate the state space here. So it would run forever, essentially. Yeah. So this is basically the trick to make this feasible. Right. So that's essentially what I wanted to show. As I said, one can now also generate, so once you've generated the state space, one can also verify these conditions here, but that's not particularly instructive because it works. So we can conclude here. So what we showed here is a way to basically take the smart contracts in DAML. First of all, provide a visual representation for them, a URL-like representation for them, and then define a way in which this can be executed in an operational model in Groove in order to verify certain properties. This is basically a case study. Okay, so there is no tool that does the mapping. We have to do that manually. We have a tool for analyzing it, but we don't have a tool for editing or creating these models automatically. So that's something that still needs to be done. We're looking at more case studies, and we're also interested in looking at quantitative analysis of these things, because often these smart contracts come together with kind of economic models. Because there is, I mean, Ethereum, for example, there's kind of a currency involved, and you can model the cost of transactions that you have to pay for and so on. So it's interesting to look at economic modeling here as well. Yeah, but I'm not going to talk about this today. Okay, thank you very much. Yeah, it's a little bit over time, but not too much.
Thank you very much, Reiko. I can clap. Thanks for the very interesting talk. Is there any question, remarks? Let's start the discussion. As usual, Nicholas, I expect that we have now some public discussion, and then we close the streaming and we may continue in private. Okay? So any question? Detlef?
Yeah, okay, thanks for the nice talk. So your case study suggests I can, or I need always a finite model. Is that true? So I cannot use Groove to represent an infinite model and do something like bounded model checking, or is that also possible?
There is also, yeah, so it's a good question. There is also bounded model checking. Well, for example, I could just have stopped after 4,000 states, and I can still do model checking with this limited transition system, but obviously that's a bit of a kind of a random way of limiting.
But that is then representing an infinite model by non-terminating state space generation process. That's a bit. So there's no finite way of representing indirectly an infinite.
Not really. So I mean, what I can do is I can generate the transition system in a bounded way. By basically saying I only want a certain number of objects of certain types, or I have certain particular strategies by which to generate this, but there is no abstraction.
So it's not because I believe, I mean, I'm not an expert on model checking, but I believe so in bounded model checking, the idea is you can have an infinite state space, but what you bound is the number of checking steps, right? So rather than the model itself.
There's a separation here. So I think the answer is no, at least in the current implementation. I think I've seen papers on this, but what is possible in the implementation here is basically you always have a separation between the state space generation and the model checking, whereas in this kind of bounded model checking, you normally have an interaction between the model checking and the state space generation, because you generate the state space where you need basically depending on the
that's the way the
formula you're evaluating. Yeah.
Yes.
Okay. Nicholas?
Thanks a lot, Reiko. Very interesting to see Groove in action. I mean, I had two questions, one a bit more practical, because I mean, you had in these constructions often some relatively complicated looking rules where you had to perform actions such as carry over all the previously incident edges to a new copy. And I was just wondering, because, you know, you said this translation is relatively manual. So even though maybe that's the intended semantics, it seems there's this alternative where you simply do not store the value. In that case, I think it was a count or something like that, directly in the node which codes for the Doodle, but have an auxiliary node which is linked to the Doodle. And then if you want to update the count, you can delete that auxiliary node and not all of the incident edges. And I mean, adjust the application constraints accordingly. I mean, it feels like maybe that was to demonstrate the capabilities, but in practice, you would try to avoid such operations, I think, where you have to manually copy over all edges, no?
It's a good question. I
mean, not that you,
there's a more efficient data structure to do this, if that's what you mean. But I mean, in the example where, for example, you have the voters list, and you need to add something to the voters list, how would you do that without copying it over? I mean, so what I could imagine is that you basically have a more complex. So what happens here is that the update operation is relatively complex.
Yes.
Then when you look up the data, everything is in one place. I think the alternative could be to have a data structure where in the new version of the data of the contract, you only represent the updated data.
Yeah.
But then you have to look back at the old version in order to collect the complete information.
I guess what you're describing.
The update is easier, but the lookup is more complex. So I think there is a trade-off here, and I don't know which is easier, but
I think also presumably in these blockchain type constructions, there are only certain operations you have available. No, I mean, it's not that you can freely design what you can look up and so on. I mean,
in the blockchain, you basically have
the history.
This is just that you just create a new basically you just create a new block and whether that contains a completely new copy, let's say, of the Doodle with all the data copied, or whether that just creates an increment in some form, say basically take the old version, refer to the old version and say, yeah, but this now needs to be updated in that way. You just store the increment. I mean, that is up to you, I suppose. That's up to how you use it.
But I imagine you have some design strategies that are favored in that
field. It could be that in the end it is cheaper not to duplicate the data, but to just store the updates. Right. But that also means that you basically, in order to find all the voters in your list of voters, you have to go through all the old versions and basically collect all of them.
Right. Yeah. And my second question was more like
in the end, maybe you don't have to find all of them. You just have to know if you just have to find out if a particular voter is on the list, and then you just have to navigate through that list of all the old versions and see if it was added at any point in the past.
Right.
Yeah. So yeah, but you're right. I mean, there may be more efficient ways of doing this, certainly in terms of the kind of duplication of information of the amount of data that you store in the graph. Whether they are easier or more complex in terms of the model, I mean, that may actually lead to more complicated rules in the end.
Yeah.
Yeah, but I mean, Groove also has path expressions, for example. So you could say in any of the old versions, is there a vote? Is that party in the list of voters? So that in principle that is possible.
And my other question was maybe more directly related to Groove itself. Is Groove capable of performing rule compositions? I mean, can I, for example, I mean, you had this package of 3 rules which sort of implements one transaction.
Yeah, no, that is exactly that. So you basically have the possibility to specify input and output parameters. I can show you them sort of quickly. Right. So how do we do that? We need to find the add voter rule here. Where is that? Let me. Okay, so that's the call rule for add voters. Okay, so what you see here, the little exclamation mark with the 0 there means that this is an output parameter. Okay, and if you have the if you look at the recipe, you see that sort of at the call add voter, which was the rule that we just said, has this output parameter as a parameter also listed there. And then you have the execution rule, which uses that as an input parameter, and the return rule, which also uses that as an input parameter. So basically, you can use these input and output parameters to specify how these how the rules overlap. Yeah, and then you could, and it's because it's a recipe, I think you can also define a function, or I think it's called a function, which would allow intermediate states, but the recipe is actually atomic.
I see.
So it's executed atomically, which means that it's really like a single rule execution in the end. I mean, it's obviously when you generate the state space, it needs to be sort of generated step by step. So it doesn't actually compose the rules. It does it sort of step by step, but in the resulting transition system, it sort of hides the intermediate states.
Right.
Yeah.
But the language couldn't allow you, for example, to check for, I mean, basically, if you want to avoid a certain negative pattern globally, you couldn't use this feature in the language, in the system, to back compose with, you know, your transition rules to check whether there can be a violation. I mean, I'm just wondering, I mean, rather than this generating a state space, I mean, is it even feasible to think about checking whether a rule can in general violate a constraint or not?
Not here. I mean, this is really a state-based analysis here. It's not.
I see.
It doesn't try to do any static analysis. I mean, it sort of does type checking and things like that, but doesn't analyze the rules statically.
Okay.
I would say this recipe essentially implements rule composition at a semantic level in terms of how it affects the transition system, but it doesn't actually compose the rules.
Right.
Yeah.
Thanks.
Okay, thanks, Nicholas. Detlef has another question.
I don't know, maybe there are other questions. I don't want to consume all the time here, but if not, then okay. So, Reiko, perhaps a general question on the style of specification here of the rule. So I must say, initially a bit surprised that, okay, I have these objects I'm interested in, so voters and parties and this stuff. And then suddenly I have to encode into the graph these operations, right? So as you explained, and they even showed up in the type graph. So I'm used to a style where, I mean, okay, I have a different background with GP, and so we have the graphs, really just the host graphs, the structure of my data, so to speak, and everything operational is specified at a different level, more like the recipes here. But so to have the analogy, we would do everything in the recipes. I don't know how powerful they are here, but I guess they're also arbitrarily powerful. So would you, I mean, do you think that's, yeah, do you have any comment on that? This mixing of that I'm forced kind of to encode my operations with the data in one graph, this mixing kind of.
You're right. I mean, that has puzzled me as well. If I remember correctly, so the main problem with just having everything in the recipe. So you could, you're right. I mean, you could try to put the control flow in the recipes rather than in the,
so this is just one more time, and then this is GP2 style, how we do it. All this stuff goes into what we call a program. It would be here, I think, recipes or big recipe or something like that. And that is completely separate. And then you have a start graph or an input graph, actually, and then the program decides what it does with it. So this is a bit, seems to be quite different from the style here.
The sort of high-level answer would be that the way in which the smart contracts and the choices are controlled in DAML is basically a different kind of control language from the control language that Groove provides.
Okay, then maybe the question is that specific here to this case study that we see these kind of graphs? So would that in other Groove applications be different?
If what you're doing, if what you want to do is essentially kind of imperative like control flow, or control flow as in sort of, I mean, maybe with kind of rule-based elements in it, then obviously you don't need those call nodes. The call nodes are there because the way in which DAML works, as I said, DAML is not an imperative language. DAML is a functional language. So basically, and so I couldn't find a good way of encoding the kind of control flow information from DAML into the control language in Groove, because they are just completely different languages.
So if DAML is a functional language, that might suggest using recursion, but I guess there's no recursion in Groove. I don't know.
Yeah. Well, in a way,
okay. Anyway, so I'm seeing this as largely here, maybe due to this specific case study and not necessarily.
So you can think of this. You can think of these call nodes as basically call and return nodes as basically implementing call stacks.
Yeah, but that is the issue. It's kind of, I have to talk actually about a kind of implementation level, if you like, control level, rather being able to just see my data and keep completely separate the dynamics. But okay, yeah, I see the point. Thanks.
I have a related question, if I can. Since you have some control structure represented in the graph, basically in the current state of the computation. So first of all, the data, as far as understood, are in a sense persistent. You cannot delete them. So this means that in the final graph after the computation, you have all the old instances of the contract, basically, all the previous versions. For what concerns the nodes, the elements of the graph which represents control, you in principle don't have this constraint, right? You can delete them. You do delete them, or you keep all of them.
What do you mean? In Groove, I could delete them, of course.
Yes, but no, in your case study, because the point is, my observation is that if you keep them, then in principle you may have some behavioral analysis of your program, also looking just at the final graph, without looking at all at the transition system by Groove, because you have all the information there, the sequence of operations.
You have all the, well, not all the information, because you don't keep information about what was created when and by which rule in the final graph, but because you delete the call edges. If we the call nodes. So if we were to keep the call structures as well in some way, then we probably have something similar to a process. Yeah, I agree. Yeah. So it's not that far off. You're right. That's I haven't thought of it like that, but yeah, that's certainly true. Yeah, and in a blockchain application, in a sort of in a smart contract application running on a blockchain, you would actually keep that because you have not just an immutable record of the data, so what we see about the data here, but you also have the record of all the operations that were executed. Yeah, so that would, in a way, be almost appropriate to keep that as well, except that it doesn't. I mean, except for analysis purposes, it isn't used or wouldn't be used. Yeah.
Okay.
Yeah, but it's a good point. Think about that. Okay.
Okay, thanks, Reiko. So I'm sorry I had to hand over possibly the chairing of the session to Nicholas because I had to teach in 10 minutes and had to rush now to the classroom.
No, don't worry.
Maybe this is also a good point to close the official session, at least, the streaming. So Nicholas, I can leave you. Thanks, Reiko, again. Thanks again. Thanks, everybody. And please, Nicholas.
Thanks a lot, Andrea. Of course, and also thanks, Reiko. I just wanted to quickly mention we are back on December 16th with a talk by Stefan Zala. And so we skip one session. And yes, I mean, if anybody still wants to have a quick chat, we stay online for a moment, and I'm just going to close the online session now. So thanks a lot, Reiko.
Thank you.
And to everyone. Thanks.